So I'm reading out some questions and see if you can do it quickly and let me know the answers, and I'll also go through it. An electric field of 640 volt per meter is desired between two parallel plates 11 millimeters apart. An electric field of 640 volt per meter is desired between two parallel plates 11 millimeters apart. What will be the voltage? So you need 640 volt per meter, and the space between is 11 millimeters. The question is asking how many volts should you apply as a potential difference. So when you read that problem and then imagine the situation in terms of a picture like this, you should be able to get the answers much faster. Yes?
Is it 7.04 volts?
I don't know the answers, but how much?
7.04. Yeah.
I don't think so. You change millimeters to meters? What formula did you use?
E equals V over D.
Okay. So V is ED, is it? And this is 640 volt per meter required between the plates. So the electric field between the plates required is 640 volt per meter. How much did you say?
Is it 7.04?
Oh, that's right. So it is 640 times 0.011. That's how we convert to meters. And then the answer is 7.0 volts. Okay. What will be the speed of a proton when accelerated by a potential difference of 500 volts? What will be the speed of a proton when accelerated by a potential difference of 500 volts? What's the speed of a proton that is accelerated by a potential difference of 500 volts? Any idea? Where do you start from? Tell me what do you start off with?
You use the formula KE equals QV, Q times V.
Yep. So the kinetic energy gained is supposed to be equal to Q, the charge, times the potential difference. And the kinetic energy is half m
V squared.
v square. And so you start from there and then Q times V. Now you start plugging in numbers. The mass of a proton will always be given to you.
Yeah, what is it?
So the mass of proton is 1.67 times 10 power negative 27 kilograms. Times velocity square is equal to charge of a proton.
1.6 times 10 to the negative
1.6 times 10 power negative 19, the same as the electron's charge. And the potential difference I said is 500. So that will get you the answers. Work it out and tell me what answer you have. much? Yeah.
3.09 times 10 to the fifth.
Are you all getting the same answers? Okay, then you should be right. So this question was asking if there is a potential difference of 500 volts and if you release a proton and if the proton accelerates, how fast will it be going by the time it crosses the 500 volts potential drop? This is an electric field of 500 Newton per Coulomb. The electric field is 500 Newton per Coulomb. And the potential at this point, is 1000 volts. The potential at that point is 1000 volts. What will be the potential (20 centimeters) from there? What will be the potential 20 centimeters from that point? So again, the electric field is 500 Newton per Coulomb, and at this point the potential is 1000 volts. What's the potential 20 centimeters ahead?
$900.
900. Excellent. How?
Since it's 500 newtons per coulomb equals 500 volts per meter, which is 50 volts per centimeter.
Perfect. Yes. 500 Newton per Coulomb is the same as 500 volt per meter. Okay? That means every meter there will be a potential difference of 500 volts. Do you understand that?
Yeah.
500 Newton per Coulomb is the same as 500 volt per meter. So that's the concept here. Very simple concept. 500 volt per meter is the same as 500 Newton per Coulomb. So when you say 500 volt per meter, if it is 500 volts over here, by the time you cross 1 meter, it should drop down to 0. And if you go another 1 meter, it should be negative 500. Yes. That's it. So, having said that, so when you go 1 meter, the potential is going to drop 500 volts, because which side is higher potential, this side or this side in a field? This is higher potential. Always field goes from high potential to low potential. So when you're going in that direction, the potential is going to drop. When you go in this direction, potential is going to go up. Get it? So the potential over here, 20 centimeters away, which is like 1/5 the total distance of 1 meter. So it's going to be 1/5 of this voltage. So it will drop by 100 volts. So from 1,000 it will drop to 900. What will be the potential on this side here at a distance of 0.5 meters? This point. How much? 1250. Do you understand the concept now? The concept is simple. 500 Newton per Coulomb is the same as 500 volt per meter. And so as you go along the field or against the field, the potential is supposed to drop if you're going along the field. If you go against the field, potential is going to be increasing. And how many times how much is going to increase is according to this. Per meter, it's 500. So depending upon how much you go. What's the potential here? If I go 10 centimeters below, what's the potential? 1,000. Yes. Potential is going to be 1,000. So if you are not going along the field or against the field, the potential is supposed to stay the same. Okay. What do you call this line? Equipotential line. Good. Okay, so you got that concept here. Good. So we are moving with the with the equipotential lines. There is no work required to be done. Only when you go against the, when you go to from one potential to another potential, then work is required. Okay. If you have 20 microcoulombs placed at the corners of a square of side 1 meter, what is the potential right in the center of the square? What's the potential at the center of the square?
0.
Think. Potential at the center of the square. I'm not asking for field. Yes, field is 0. If I ask for field, that's 0. Why? Because if I put a unit positive charge over there, this will push it in this direction, this will push it in that direction, that will push it in this direction, this will push it in that direction, so the net force is going to be, so electric field is 0, yes, potential is not 0. How do you find the potential? Make sure I'm taking the video, so you missed a couple of things.
Yes, sir.
I'll put it on Rockspace, you can check it out and find out what you missed. Okay?
Yes, sir. Thank
All right. Yes.
It's like 509,000 volts or something.
I don't know the answers, but if there is a common answer, then I can just agree with it. So he's got some answers, let's see. So to find the potential over here, tell me with the plan, what did you do?
I just took out the potential of one of them from these and then multiply by 4.
That's it, that's all you have to do. Find the potential from one of them to here, and then just multiply by 4 because it's going to be identical, right? And potential being a scalar quantity, just add those quantities as it is. So to find the potential at this point, you need this distance.
No, I did.
You need this distance, which is half of the diagonal. The diagonal is 1.414, so this must be 0.707, right?
Yeah.
1.414 is the square root of 2. That is this. So 1 square plus 1 square is square root of that, Pythagorean theorem. And then this is going to be 0.707. So use that and find the potential here by using the equation K Q over D. And then you multiply by 4 because it's, so you do this 9 10 power 9 times 20 micro divided by D, which is 0.707. And then once you get the answer, multiply by 4. What is it?
It's 1.01 times 10 to the 6.
Have you multiplied by 4 already?
Yeah.
So this this whole thing times 4. How much is that? 1 point?
Go 2 times 10 to the
Negative
negative 6.
6?
I mean 6. I will. Not negative 6.
6
Yeah.
volts. So it's a million volt at that point.
So,
I'm not sure of the calculations, but if you all agree with it, then it's fine. If a capacitor has opposite 5.2 microcoulomb charges on the plates and an electric field of 2 kilovolt per millimeter is desired between the plates, what must each plate's area be? So let's do that. Again, if the charge on the plates are supposed to be 5.2 microcoulombs, so the charge is 5.2 microcoulombs. And the electric field desired is 2 kilovolt per millimeter. The electric field desired is 2 kilovolt per millimeter. What should be the area of each plate? That's a question. What formula are you knocking on?
Is it C equals Q divided by V?
Say it again.
C equals Q divided by V.
Okay. Then what do you do?
Then you, I mean, you can convert that. So it's I named it Q divided by C equals V. So that's what you do.
Okay. Where's the area coming in?
You're right.
We need the area somehow, right?
is C equals area.
Yes.
C equals epsilon area over distance.
C is equal to epsilon area over distance. Where is C?
5.2.
No, that is charge. C is measured in farads. This is charge Q. Yes. What did you do?
It's E equals Q over epsilon A.
Yeah, this one, right? Is that what he did?
Yeah.
Yeah, so basically this is a charge density on the top, which is basically Q over A epsilon. They gave you this, they gave you this, they give you know, what is epsilon r? You can find the area. You get it? Have you seen this equation before? Yeah. Electric field is the charge density over the epsilon permittivity. And electric field is Q, the charge density is Q over area. So we have that. Now the electric field is not given in the right unit, so you have to take care of that part. So 2 kilovolt, which means 2000 volt per millimeter. Is that per meter? So what do you do? Conversions. Be careful. You know, these conversions you should be careful because you can go one way, opposite way. So millimeters to meters, is the unit going bigger or smaller? The unit is going bigger, so the number has to go how many times smaller? 1,000 times smaller. So now we do have this. Now you got it in volt per meter now, which is 2,000. That's why I said, you know, when you do these conversions, there's a chance that you go the opposite way, and then you end up getting 2 volt per meter. So it is 2 million. Is equal to charge 5.2 micro divided by area times epsilon naught 8.85 times 10 power negative 12. And then you can find out area.
Is it 0.294 meters squared?
I don't know the answers, let me see. Yes. 0.294 meters square. That's the area of the plates. Yeah.
Can you repeat what the top variable is called above epsilon?
This is called the charge density. So sigma is a charge density, which is actually how much charge is there per surface area of A. Okay? So if there is a charge sitting on this table, what is the charge density? It is the charge divided by the total area of the table. And that divided by the epsilon naught will tell you how much field is coming out of the table. Do you understand? So any charged surface is supposed to spit out electric fields. And how much electric field is coming out from it? That much. Yeah,
Is that the area of both plates, or is that just the area of one?
one. The common area. You know, if it is like that, there's no area at all. So it's just the common area that matters. Any questions on this? It's fine. The 9,500 picofarad capacitor holds a charge of 16.5 times 10 power negative 8 coulombs. What's the voltage across the capacitor? And 9,500 picofarad capacitor holds a charge of 16.5 times 10 power negative 8 coulombs. What is the potential difference applied? So that's a charge sitting on it. That is the capacitance. So this is the capacitance, and that is the charge. They're asking for V. That should be straightforward. Answer is
17.37
so. That should be the answer. The simple equation Q is equal to CV.
We'll take you there. All right. Okay. Pico 10 per minus 12. Okay. 17.4. What? Wait a minute. A 3,500 picofarad capacitor, air gap capacitor. A 3,500 picofarad air gap capacitor is connected to a 22 volt battery.
A 3,500 picofarad capacitor is connected to an air gap capacitor, which is connected to a 22 volt
Supply. A 3,500 picofarad air capacitor is connected to a 22 volt battery. If a piece of mica is placed between the plates,
If a piece of mica is placed between the plates,
how much charge will flow from the battery? How much charge will flow from the battery? That's a question. And of course, you need the information about mica. What do you need about mica? You need the dielectric constant or relative permittivity, which is 7.
so the epsilon R or K for mica is 7.
So what's the question asking you to do? You connected this one to the air capacitor, and then the mica part of it is introduced. As soon as the mica is introduced, what's going to happen is more charges will actually start flowing from the battery into the capacitor. How much charge actually flowed? How much charge really went into the capacitor? So what is your line of attack? Ben, any ideas? How do you start off this? Again, it's an air capacitor connected already to 22 volts. It stays like that, it's fine. But when mica is introduced, then more charges will start running in. We saw that last class, right? Capacitor connected online. So when mica is introduced, immediately more charges will start flowing in. How much charge actually flowed in? How much charge will flow from the battery when the mica is introduced? Yes. What do you do?
Is that 1300 picofarads?
Yes, that's piping. Yes.
And then
Say it again.
is that before the mica is introduced?
No, that's a capacitance. Yeah, before. Yeah, that's before. The 3,500 air gap capacitor. So that was what it was before. This was a capacitance of the air capacitor, not with the mica. What will happen with the mica? What will happen to the capacitance with the mica?
It will increase by factor 7.
It will increase by factor 7. So this times 7, that's a new capacitance. So it has an old capacitance of this. And when the mica is introduced, the capacitance changes to a new one, which is what? The new capacitance is 3,500 times 7. That's a new capacitance. And the question is asking you, how much charge will flow in extra, right? So for that, okay, what was the previous charge? You have to find that out and find the new charge. and then you can actually subtract. So the equation is Q is equal to CV. The previous charge is 3,500 picofarads times the potential difference of 22. That's the previous charge. What is the new charge? New charge is 3,500 times 7 times 10 power negative 12 times 22. So how much is the charge that is flowing in extra? It is this, right? That's extra charge, which basically is this minus this. So it will be 3,500 times 6 times 10 power negative 12 times 22. So when you subtract 7 times this part minus 1 times this part, you'll get 6 times that part.
4.62 times 10 to the negative 7.
I don't know the answers here.
I get the same answer.
You got it? Okay.
Just subtract the old capacitance from the new, or the old charge from the new charge.
Are you confused on the 6?
I just think that they got the keep on subtracting that.
You find this answer and subtract. That should give you that. Yeah.
Can you explain again why you'd times it by a factor of 7?
Because when you introduce the dielectric, you know the capacitance is equal to epsilon naught A over D.
It's 12.
The new capacitance is going to be epsilon naught epsilon R A over D.
Oh, okay. That makes
So it is going to increase by that factor of 7. The capacitance, the new capacitance is going to be that many times the old capacitance. Okay? Yes, Jared.
I'm confused about where the 6 came
Yeah, 6. Okay, I'll show you that. Instead of doing this and doing this, what I did was this. Can you see this whole thing here?
Yeah.
And you can see, okay, if I pull the 7 out, probably you'll understand. Times 7. Now this is times 1. Now when I subtract this from this, it's like 7x and 1x. What is 7x minus 1x?
That's it.
That's what it is. 6 all. Got it? So instead of doing both of them separately, you know, when you know that that is a common factor, then just take it off. All right. Any questions on that? Everything's okay? A parallel plate capacitor has a charge of a fixed charge of Q coulombs. The separation of the plates is then doubled. A parallel plate has a fixed charge of Q coulombs. When I say Q, it's automatically like plus Q and minus Q. You know, don't get confused of the plus Q and minus Q. If one plate has to be charged, the other one automatically gets the opposite charge. Okay? So sometimes they'll say this has got plus 100 microcoulombs, that's got minus 100 microcoulombs. You just take it as 100. That's it. You don't have to worry about the charge on the capacitor. It's 100. So Q. The separation of the plates is then doubled. I think we discussed this towards the end of the last class. The separation of the plates is then doubled. Question A. By what factor does the energy stored in the in the electric field change? I don't know why they say electric field. By what factor does the energy change? That's enough. You don't have to worry about the electric field. By what factor does the energy change? So the charge stays the same. The distance is doubled. And you know the energy formula is? In terms of Q, it is Q square over formula. What's the energy stored in a capacitor? Formula. I gave you 3 forms of the energy. Yeah. Q square over 2C. The energy formula, energy is QV, half QV, or half CV square, or Q square over 2C. These are the energy stored in the capacitor formula. So looking at that formula, this is the energy stored here. And what's the energy stored on this one? It is Q square, no change to that, divided by the 2C prime. What's happening to the C prime? What is the new capacitance when the distance between the plates is doubled? Halved. So the distance between the plates is doubled, the capacitance is halved. So this is the same as Q square over 2 times C over 2. Right? Capacitance is halved. So basically that means it's going to be 2E. You see it? This part is E. And you can see this part here, which is E, divided by 2 here, so it goes to the top, so 2E. So the energy is doubled, simple. The second part of the question says, how much work must be done in doubling the plate separation from D to 2D? How much work must be done in doubling the plate separation from D to 2D? They're asking you that in terms of D and area. So they want it in terms of area. So the area of the plates is A. So what is the amount of energy? The thing had energy of E before. Double the plates. The total energy is what? So how much work was done? How much work was put in? Come on. It had energy E. Then when the plate separation was doubled, now the energy is 2E. How much work was done? E. That's the amount of work done. It's like this already has 100 joules. Now it has 200 joules. How much work was done? 100 joules. The difference. So the amount of energy that was put in, or the amount of work that was done, is E itself, and which is what? Q squared over 2C. So if you want to bring it in terms of Q and area and all that, get rid of the C. So it's going to be Q squared over 2 times, what is C? It is epsilon naught area over D. So we have that equation. So that is in terms of area and the distance and the charge. So that's the amount of work that has to be put in. Oh, yes.
What does E represent?
Energy.
Oh, okay. I was saying
Easy energy.
that's
The energy stored in a capacitor is the same as the amount of work required to put those charges there. Okay? Next one. A 2.5 microfarad capacitor. A 2.5 microfarad capacitor a 2.5 micro, where is it? Lost it. A 2.5 microfarad capacitor is charged to 875 volts. A 2.5 microfarad capacitor is charged to 875 volts. And a 6.8 microfarad capacitor. And a 6.8 microfarad capacitor is charged to 652 volts. A 2.5 microfarad capacitor is charged to 875 volts, and a 6.8 microfarad is charged to 652 volts. These capacitors are then disconnected from the batteries. So this one is connected to a battery, this was connected to a different battery. Now they're both disconnected. Now these capacitors are then disconnected from the batteries. Next, the positive plates are connected to each other. The positive plates are connected to each other, and the negative plates are connected to each other. The positive plates are connected together and the negative plates are connected together. What will be the potential difference across each capacitor and the charge on each capacitor? What will be the potential difference across each capacitor and the charge across each capacitor? We have not done anything like this before, so just pay attention to it. So I'll solve it right here. Tell me what will happen if you connect it like this. What will happen technically? Will anything happen at all, or is something going to happen other than explosion or whatever? Is anything going to happen when you connect it like that? Okay, so when it is charged here and charged here, that's fine. It stays charged. So we have one capacitor We have one capacitor like that, there's another capacitor. They will stay like that. But the moment you connect wires, what do you think can happen when you connect wires? Yes? The one with the higher charge will charge the lower one. Until when? Until they both get equal charges?
Until the voltage is equal.
Until the
Potential difference.
potential difference. So, what's going to happen here? Which one has got more potential difference? This has got more potential difference. This has got less potential difference. Which way is the charge going to flow? This way. So this is going to lose charges, and this is going to gain charges. It's like two tanks. It's like two water tanks. This is a water tank. This is another water tank. The water tank has got this much. This one has got this much. Now when you connect them by means of a tubing, when you connect the two tanks with the tube, what will happen? These markers. Okay, so when you have this tank connected to this tank, this is the amount of water. So when you connect the two tanks together, what will happen? Water will flow from where to where?
The left is
From the left to the right, water is going to flow. Until when?
oh, thanks for your service.
Until, alright, let me make this narrow, just for a comparison. Alright, I'm making that a little narrow, so water is going to flow that way. Till when? Till both have the same quantity of water, or both will reach the same height? Same height. Yeah, not quantity. This cannot have the same quantity as this. It's a narrow one. Okay, I'll make it still narrow for your comparison. Now, what's going to happen is this going to push a lot of water out into that? Or this will push some water and this will start climbing up to somewhere here, and this will drop from there to here, and will stop there. No more flow. Why? There is no what difference? Yeah, potential difference or pressure difference. So the pressure here and the pressure here is not going to change. Going to stay the same. So until the potentials are exactly the same, the flow will take place. We'll see about fluid dynamics later on, right? So there you'll learn more about these things. But that is the concept here. This has a potential difference of 875. This has a potential difference of 652. So what's going to technically happen is charges are going to move from here to here. That's for sure. Until when? Until they both reach a common potential difference. You understand? Alright, before you go ahead with this one, we need to find out how much charge is sitting here. Can you find that out? What's the charge on this plate? What is Q here? Let's call it Q1. How much is Q1? What's the charge on the first plate?
So 2.19 E minus 2
2.19 times 10 to the power of
minus 2.
coulombs. 2.19 times 10 to the power of minus 2 coulombs.
It's minus 2 minus 3. Yeah.
How much?
Negative
-3. Okay. Alright. So 2.19 times 10 to the power of negative 3 coulombs. That's right. Now what's the charge sitting on this one? Q2. What's the charge on the second capacitor? Yeah. 4.43 times 10 to the power of 4.43 times 10 to the power negative 3 coulombs. That's a charge sitting on this. Now what is going to happen? Which one is going to push more charge? Is this going to push the charge that way, or that is going to push the charge this way. Huh? It's like going back to the water tank. This has got this much water. This has got that much water. Tell me which one has more water. This has more water, this has more water. This has more water, right? But when I open this tap, which way is the water going to flow? To the right or to the left? To the left. This is going to come down and this is going to go up. You understand that? So it's not the quantity that matters, it is the potential difference that matters. Okay? So in this case, this one has got more charge. This has got less charge. But what's going to happen when you connect it? This is going to lose some more charges into this. And this one is going to gain charges. So after some time, this is going to change from Q1 to Q1 prime. New charge. This is going to go from Q2 to Q2 prime. New charge. And when will the charging process stop? When the potential difference will become common. Now this is 875. This is 652. So what's going to happen is charges are going to go from here to here. So this is definitely going to increase from 4.43. This is going to drop from 2.19. But eventually what's going to happen is both will have some charges, but this 875 is going to drop to some new value. The 652 is going to build up to some new value, and this is a new value. They're asking you to find this and this, the new charge. So how do we go about this? What we do is this. Q1 prime and Q2 prime, we have no clue about each one. But one thing is definite. Q1 prime plus Q2 prime should be equal to the total charge that's already there, right? It's only a give and take. The charge cannot be created nor destroyed. They only kind of flow from one place to another place. So if some coulombs are going down here, okay, this is going to go down here. So this gains some charge, that loses some charge. The total charge is supposed to be how much? Add them up. What's the total charge? 6.62 times 10 to the power of negative 3 coulombs. That's a total charge. Now, can you get me an expression for Q1 prime in terms of the new voltage V? In terms of the new voltage V, can you express Q1 prime the same way as you found this charge Q1? What is Q1 prime? Isn't this C1 times V? Yes? And what about the other one? It is C2 times V. So C1 times V plus C2 times the new voltage, which is both V's, is equal to 6.62 times 10 to the power of negative 3 coulombs. And you know C1 and C2. So if I take V common, we get that. And so now C1 is 2.5 and C2 is 6.8 micro is equal to 6.62 times 10 to the power negative 3. So you can solve for V. How much is it?
711.83.
711. So 712 volts. Must be right, because you're anticipating that 875 should drop and this 652 should go up. So 712 should be a reasonable answer there. You understood what we did, right? Okay. You should be able to do them. Please open now. You can try this out yourself. A 2.7 microfarad capacitor is charged by a 12 volt battery. A 2.7 microfarad capacitor is charged by a 12 volt battery. It is disconnected from the battery and then connected to an uncharged 4 microfarad capacitor. A 2.7 microfarad capacitor is charged by a 12 volt battery. And then the battery is disconnected and connected to an uncharged 4 microfarad capacitor. Determine the total energy stored before the capacitors are connected and after. Determine the total energy before they're connected and after. So you need to find out the total energy before and after. This is uncharged. What's the potential difference? 0. So find out the total energy before, which is much easier. What is the total energy before? Yeah.
CV squared over 2.
Yeah, CV squared over 2. Half CV squared. Because this has no energy. This is the only one which has energy. How much is it? How much is half times 2.7 micro times 12 square? You can express in microjoules. That's fine also. How much? 30? What? How much do you have? Say it.
I
Somewhere.
guess 2.3 times 10 negative. Is that energy before? I don't know if that's right.
Maybe, yes. 2.3 times 10 power.
Negative 3. That's what I said. I don't know.
Just check again. Half CV square. All you're doing only is half CV square. Not a big deal. Half of this times 12 square. 1.9
times 10 power.
negative. That looks right. Okay. That seems okay. Yeah, 1.94 10 power minus 4 joules. That's the energy before. Now, how do you find the energy after? What do you need to do? You need to do exactly what we did in the previous problem. We need to find out the new voltage. We need to find both of those. Huh? This one, half CV squared. Half times 2.7 micro times 12 squared. The energy stored in this capacitor is half CV squared. That's a formula. So that should be right. Now, how do you find the energy after? You have to find the new voltage just like how we did the previous problem. So how much is the charge sitting here? Be quick. How much is charge sitting there? And how much is the charge sitting here? 0. How much is that charge sitting there? How much?
2.24 times 10 power negative.
Negative? So that's the energy, that's the charge sitting there on the top one. And the charge sitting here is 0. But you know that when you connect them together, when you connect them together, this charge, this is 12 volts, and this is nothing, so it's definitely going to flow in here. So this is going to have a new charge Q1 prime, and this will get a new charge Q2 prime, such that Q1 prime plus Q2 prime is equal to 3.24 times 10 to the power of negative 5. Same approach as what we did earlier. And this one is Q1 prime is C1B plus C2B is equal to 3.24 times 10 power negative 5. So B times C1 plus C2. C1 is 2.7 and C2 is 4.0 times 10 power negative 6 is equal to 3.24 times 10 power negative 5. So what is V?
Is it 4.84?
Could be 4.84 volts. Now that you have found V, can you find out the new energy after you connected it? Find the new energy. So new energy is going to be half C1V square plus half C2V square. The same voltage, both of them are going to have the same voltage as 4.84, but it's going to be half C1V square plus half C2V square. So do this up and tell me how much you get. This will tell you the total energy after you connected it. What is the total energy after? Half C1 V square plus half C2 V square should be equal to half 2.7 micro times 4.84 square plus half 4 micro times 4.84 square. If you want, actually, you can put them together. This is half 6.7 times 10 power negative 6 times 4.84 square. How much is it?
Where do you get the food?
He told me, I don't know.
Oh.
From here. That divided by this. So 3.24 10 power minus 5 divided by that should, yeah, looks right. How much is this?
Yeah.
7.85 times 10 to the power of negative fifth, which is same as 0.785 times 10 to the power of negative 4 joules. I'm just writing it like this so that you can compare. What was the energy before? 1.94 10 power minus 4. What's the energy after? 0.785 times 10 power negative 4. Did it lose energy or gain energy? It lost energy. Where did it lose the energy? You know, energy is supposed to be conserved, right? The total energy is supposed to be conserved. What happened over here? Where is it lost? Can you account for the difference?
The resistance of the wire.
Say that again.
Resistance of the wire.
What will it do?
Heat up.
Heat up. That's it. This, when the charges were moving from here to here, it is moving through a wire with the resistance, which means it will cause heating effect. This wire will get slightly hot because there is a flow of current. And because of the flow of current, there is some heat dissipation on the wires. And how much heat is dissipated is the difference. Can you see that? Okay, so I think with this sort of practice, you should be in a very good position to answer your test comfortably. But be fast, because you need to work with stuff. and practice these questions again, because then you will be moving at a faster rate. Good. I'm posting